So let's go ahead and get started. Last time we talked about uniform flow in open channels. So we're in our last module of the class focusing on open channel flow. And the first topic that we looked at was uniform flow. This is a very widely used case. You'll encounter it a lot if you do any kind of stormwater design, hydraulics and hydrology design in the civil engineering field. So just remind me, what are some conditions that characterize uniform flow? We talked about 2 or 3 definitions of uniform flow that are equivalent. So how can we define or characterize uniform flow? Oh, yes. The water depth is the same. So the first condition that characterizes uniform flow, and probably the definition that you'll see most commonly, is that uniform flow is the case where the depth and velocity of flow do not vary over the length of the channel. So the depth and velocity remain constant throughout the channel's entire length. Basically, if you have that condition, the only thing that can happen is that you have the water surface is parallel to the ground surface beneath it. So that's one way we could characterize uniform flow. I talked about a couple other ways that we could characterize uniform flow, specifically looking at the force balance. So what's another way, an equivalent way that we can characterize uniform flow?
Force is going to be equal to the friction.
Okay, very good. So those are the 2 other conditions that we can use to characterize uniform flow. The first is that the bottom slope of the channel is equal to the friction slope. And this gave rise to the form of Manning's equation that we're going to be using to solve these uniform flow problems. The bottom slope is equal to the friction slope. And again, that friction slope is equal to the energy loss or head loss per unit length along the channel. So for uniform flow specifically, the bottom slope of the channel is equal to that head loss per unit length. And as you mentioned, that is equivalent to saying that the gravitational force is exactly balanced by the frictional force. So for uniform flow, there are only 2 net forces that are non-zero. There's the gravitational force and the frictional force, and those 2 forces balance each other exactly. All right, so we talked about uniform flow, what characterizes it, and using this second characterization specifically, we came up with an equation for relating the depth and the discharge in uniform flow. Does anyone remember what that equation was called? Does anyone remember what that equation was called? Manning's or Manning's equation. So this is the most widely used equation for uniform flow, at least in the United States. So it takes the form of this equation here, usually with discharge as the dependent variable. So Q here is our discharge, and it's relating that discharge to the depth of water in the channel and the hydraulic geometry that that depth defines. So we have the discharge as our dependent variable. This S naught, this is the bottom slope. This is something that can be measured or surveyed. A is the cross-sectional area. And again, this is a function of the depth. R is the hydraulic radius. Again, this is a function of the depth of water. What is this N here? Okay, this is the Manning's roughness coefficient. So this characterizes the roughness of the channel material. And then this phi parameter is a parameter that depends on the unit system we're in, because Manning's equation is not dimensionally consistent. Phi is equal to, sorry, this is wrong. This should be SI, this should be SI units on the top here. So it's 1 for SI units and 1.49 for US units. So if we have SI units, the discharge will be in what units? Cubic meters per second. If we're in US units, that discharge will be in cubic feet per second. So remember, there are certain units that we have to use with Manning's equation. All of the dimensions will be either in feet or meters. The flow rate will be in cubic meters per second or cubic feet per second. So we applied Manning's equation to compute both the discharge and depth in prismatic channels. Under uniform flow conditions, we looked at a rectangular channel. We looked at how we could compute the discharge given the depth in the channel, and we looked at how we could implicitly compute the depth given the discharge in the channel. And towards the end of class, I gave you an example exercise to work through performing those same computations for a trapezoidal channel. So we looked at computing uniform discharge and the normal depth in prismatic channels for often in hydraulic design, especially for natural channels. You'll also need to perform these same computations for irregular channels. So what I want to do next is I want to go through an example looking at how we can compute the discharge and the depth. For this example, I'm just going to show you how to compute the discharge, but we're going to consider an irregular channel. Again, this is something that you might encounter if you're dealing with natural rivers or other channels with floodplains. So let's consider the following irregular channel. So we're going to consider the irregular channel shown below with a bottom slope S naught of 0.004. So our channel is going to consist of two sections. We will have a trapezoidal section that looks like this. And then we're going to have a rectangular section that looks like this. So let me just divide this up here. And there's going to be some water level in the channel. Bless you. So we have two different sections here. Our rectangular section, it might be, for instance, a floodplain. So it's going to have a grassy bottom. And let's just say that the wall on this side also is vegetated. And due to this vegetation, that's going to have a relatively high Manning's roughness of N2 is equal to 0.05. So the right side of the channel is going to be grassed. The left side, this concrete portion, it's going to be made out of concrete. Yeah, this wall is going to be concrete as well. And this section here will have a roughness of 0.014. So that's value that's typical for concrete. Let me give you the dimensions of the different parts of this channel. So for this trapezoidal section, this bottom width here, this is going to be, I'm going to call this B1, and this is equal to 2 meters. The top of this trapezoidal section, this is going to have a width of B2 is equal to 6 meters. The width of this triangular portion here is going to be 2 meters. On the other side, the width of this triangular portion is also going to be 2 meters. I don't know why I drew it like that. Let me get even with these other markings. The height of this triangular portion here, this is going to be H1 is equal to 1.5 meters. The height of this portion right here, this is going to be H2 is equal to 2 meters. So I'm talking about this height here from the top of the trapezoid to the water line. For the right side of the channel, this width here, this is going to be B3 is equal to 10 meters. That should be all the dimensions that we need. And what I want to do is I want to compute the total flow rate, assuming uniform flow. So we have the bottom slope, we have the depth of the water, we have the dimensions that define the geometry of the channel. And what I want to do is I want to compute the total discharge. So how might we go about computing the total discharge for a non-prismatic geometry like this? Yes. Yes, you can split it into different shapes. So that's how we're going to do it. So I'm going to split this into two shapes here. I'm going to call this section on the left, everything to the left of this yellow line, I'm going to call this section 1. And everything to the right, I'm going to call section 2. Just a note before I move on, we might want to know the side slope of this trapezoid. So you'll note that the triangle here is 2 meters wide and 1.5 meters tall. So our side slope in terms of the horizontal to vertical dimension, this will be 2 divided by 1.5 is equal to about 1.33 repeating. So we'll need that side slope for computing the perimeter and cross-sectional area of this trapezoidal portion. So let's go ahead and try computing the discharge. I'm going to look at section 1 first. And let me write out all of our dimensions here. We have B1, the width of the bottom part of the trapezoid. This is 2 meters. H1, the depth or the height of that trapezoid is going to be 1.5 meters. B2, the top width is going to be 6 meters. H2, the height of the rectangular portion above the trapezoid is going to be 2 meters. And the side slopes of the trapezoid are going to be about 1.33. Okay, so first let's compute the area. So looking back, there's two parts to this shape. There's the trapezoidal part here, and there's the rectangular part above it. So I'm going to get the area by summing those two shapes together. So for the rectangular portion, we have B2 times H2. And to that, we're going to add the area of the trapezoidal portion. So from our table of hydraulic geometries, the formula for the area of a trapezoid is given by the following. H1 times quantity B1 plus side slope M as in mountain times H1. So this is our total area for this section here. If we substitute in our known values, so B2 is equal to 2 meters, H2 is equal to 2 meters. Sorry, B2 is equal to 6, not 2. So it'll be 6 times 2 plus 1.5. That's H1 times quantity 2 plus 1.33 repeating times 1.5. And if you evaluate this expression, you should get 18 square meters for the cross-sectional area of the left side. Yes. Sorry? Wouldn't it? So the horizontal dimension is 2. The vertical dimension is 1.5. So when we were writing the slope here, we're expressing it in terms of our convention as horizontal to vertical. So 2 is greater than 1.5, so it has to be greater than 1. So it turns out this slope is 1.33. So this equation here assumes that that slope is written horizontal to vertical. Okay. Did that answer your question? Yes. Well, you would just use a different form of this equation here. So you could write this equation as 1 over m instead of m, if your m is vertical to horizontal. But just for simplicity here, I'm using horizontal to vertical. All right, so the area is 18 square meters. For the perimeter, we're going to need to add the height of this wall to the perimeter of this trapezoid. So that's going to be H2 plus B1. So that is the bottom width of the trapezoid plus the 2 hypotenuses of that trapezoid. So this is going to be 2 times the square root of m as in mountain squared times h1 squared plus h1 squared. We substitute in our values, we get 2 plus 2 plus 2 times the square root of 1.33 squared times 1.5 squared plus 1.5 squared. That should give us a perimeter of 9 meters. So let's do these same geometry calculations for the right side. For section 2, let's write out our dimensions here. So B3, the width of that rectangle is 10 meters. H3, the height of the water in that rectangle is 2 meters. So for the area, it's not too difficult. All we need to do is multiply B times H. So the area of the second section is going to be B3 times H3 is equal to 20 meters squared. For the perimeter, what is the perimeter going to be equal to? Looking back at our drawing. 2 plus 10, right? So we don't count the left side of this rectangle because there's no surface there. So it's just going to be equal to B3 plus H3, which is equal to 12 meters. All right, so once we do this, we compute the discharge within each section, and then we can just add those discharges up. So let's plug each of these areas and perimeters into Manning's equation. So for the first section, the discharge will be equal to phi over n1 times a1 to the 5/3 power divided by p1 to the 2/3 power times the square root of the bottom slope. We substitute in our numeric values, we get 1 over 0.014. Our area is 18 square meters. We raise that to the 5/3 divided by the perimeter is 9. We raise that to the 2/3 times the square root of 0.004. And if we evaluate that expression, we should get a discharge of about 129 cubic meters per second. For the discharge in the second section, same deal. We take the parameter phi divided by n2, the roughness in the second section, times a2 to the 5/3 divided by p2 to the 2/3 times the square root of the bottom slope. If we plug in numbers, we get 1 over 0.05. So we have a different roughness in the second section, times 20, the area to the 5/3 divided by 12 to the 2/3 times the square root of 0.004. If we evaluate that expression, we should get about 36 cubic meters per second. So you can see that the discharge in the second section is actually quite a bit lower, even though it has a large cross-sectional area. And that's partly due to the fact that it has a much rougher surface. So the higher roughness is going to decrease the discharge for a given depth. So if we want the total discharge, we just add up these two individual discharges. So Q, the total discharge is equal to Q1 plus Q2. And that is equal to about 165 cubic meters per second. Right, so there will be a homework problem on homework 6 that is pretty similar to this one. So make sure you're comfortable with this approach. To compute the discharge in an irregular channel cross-section, we just break it up into pieces that we can analyze, and then we add those individual discharges together. So this is actually the same way that the discharge would be computed in a computer program like HECRAS, which you'll be looking at in Lab 5. All right, any questions on this problem? Not too bad. All right. Oh, yes. Mhm. It's so it's equivalent because R is just A over P. So there may be situations where you have R pre-computed for some reason, and then it might be more efficient to use R. Yeah. Good question. All right, any other questions on this example or uniform flow in general? We're going to be moving on from uniform flow after this, so any conceptual questions about uniform flow are welcome. Yes.
That perimeter equation, it's on the references, right?
For this example, we had to just think about the perimeter. So we had to add the perimeter of that trapezoid to the wall. So I would just look at the diagram and try to figure out what the perimeter would be using the equations that you have available in the reference table. All right, so we're going to be moving on from uniform flow. It's going to keep coming back throughout the rest of the course, but I want to talk a little bit more about more sophisticated flow conditions. So uniform flow is the simplest case that we can reason about. So it's the case where the depth and velocity do not vary throughout the channel. And it typically occurs in situations where you have a very long channel with a relatively constant slope and no changes in the channel geometry. So that's often useful if you're talking about something like a gutter or a stormwater channel, or maybe a river. You can approximate it using uniform flow conditions, but anytime that you encounter changes in the channel geometry or changes in the bottom slope, the uniform flow condition will no longer be a good model to use. So I want to talk about what happens when we encounter changes in the geometry or changes in the bottom slope or the bottom surface and how that affects the flow in the channel. So what I want to do first is I want to give you a mystery problem. So let's consider flow in a channel. So we're going to have some depth of water in the channel. This is a horizontal channel. And the bottom of the channel has a bump in it. Okay, so at the upstream end, we'll have some depth h1, some velocity u1. We're assuming steady state conditions here. And the channel is horizontal until it encounters this bump in the bottom. And let's say that this bump has a height of delta z naught. So the flow is moving in this horizontal channel and it encounters this bump. So what I want you to tell me is, what do you think is going to happen to the water surface elevation when the water encounters this bump in the channel? So there's three basic things that can happen. It could go up, it could go down, or it could stay the same. So let's take a vote. Who thinks that the water surface is going to go up when the water encounters the bump? And you have to answer one of these options, okay? So we have quite a few votes for water goes up. So let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Say about 26 think that the water surface is going to go up. Okay, who thinks that the water surface is going to go down? Raise your hands high. Be brave. Okay, 1, 2, 3. Any more? 3, 4. Okay, we got 4 for water surface goes down. Who thinks the water surface is going to stay the same? Okay, so we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 15-ish think that the water surface is going to stay the same. And independently of each of these answers, who thinks that this is a trick question? Okay, who thinks that I'm just messing with you? Okay, so we got quite a few votes for this is a trick question. So for those of you who think it's a trick question, why do you think it's a trick question? Yes.
Might go down.
Okay, might go down and then up. Any other ideas? Yes. It's April Fool's Day. That's a good one. So no, I did not just create this problem for April Fool's Day. So this is a real situation. Okay. So we'll figure out shortly which of these options it is. It might not be obvious what happens, and your intuition may lead you astray here. So basically we have the depth and the velocity at the upstream end of the channel. What we want to do is we want to predict the depth and by extension, the velocity at the point where the water encounters the bump. So we have depth and velocity at the upstream end, depth and velocity at the bump. How could we go about analyzing this problem? What equation might we want to use here? Continuity. So we'll use continuity implicitly, energy. So yes, we will end up using the energy equation. It's always a good guess in this class. So let's try applying the energy equation. It will turn out that we don't have enough information yet, but let's go ahead and try. So we have the depth at the upstream end, the velocity at the upstream end. We have the depth at the bump and the velocity at the bump. So let's write out our energy equation. We have Z1, the bottom elevation at the upstream end, plus H1 plus U1 squared over 2G is equal to Z2 plus H2 plus U2 squared over 2G. Oh, and there's one thing I forgot to mention. So we're looking at a relatively short distance, so the frictional losses are negligible. And this is a smooth transition, so we're not going to encounter minor losses. So we're going to assume no energy losses. Okay, so we have that the energy at the upstream end is equal to the energy at the bump. You'll notice that Z2 minus Z1 will be equal to the height of the bump. So we can rewrite our energy equation as H1 plus U1 squared over 2G is equal to H2 plus U2 squared over 2G plus delta Z naught. And to go any further, we're going to need to add some numbers. So let me put some numbers defining the channel geometry and the upstream conditions. So we're considering a 3-meter wide channel. So this is a 3-meter wide rectangular channel. It has a bottom ridge in the middle of the channel. So the ridge is delta Z naught is equal to 0.3 meters high. Upstream of this ridge, so upstream of the transition, the depth of water H1 is equal to 3 meters, and the velocity U1 is equal to 3 meters per second. And we're going to assume no energy losses. So what I want to do again is to determine the height of the water surface. So that'll be H2 plus delta Z naught. So this is the water surface at, so I'll say water surface elevation at the crest of the bump. And I want to determine whether it goes up goes down or stays the same. So the first thing that I'm going to want to do here, it's going to be useful to compute the discharge. So I'm going to do that first. So just looking at these quantities here, can anyone tell me what the discharge is? It's a nice integer value. This is a rectangular channel. 27. Very good. So it's going to be the width of the channel times the depth of the water times the velocity. So that's 3 meters times 3 meters times 3 meters per second gives us 27 cubic meters per second. So we're going to need this for later. Let's go ahead now and plug in some of these values into our energy equation. I'm going to rearrange things first so that we can specify everything that we know. So going back to our energy equation, we have H1 plus U1 squared over 2G is equal to H2 plus U2 squared over 2G plus delta Z naught. So we know H1, we know U1, we don't know H2, we know delta Z naught, and we don't know U2, but we know the discharge. So let's go ahead and let's rewrite this expression here in terms of the discharge. So we'll have H1 plus U1 squared over 2G is equal to H2 plus quantity Q squared divided by 2G times the cross-sectional area squared. Cross-sectional area will be bottom width times H2 all squared. And to this, we're going to add delta Z naught. So note that here, what I've done is I've taken U squared is equal to Q squared over A squared. So that's where this here is coming from. Let's go ahead and plug in our numeric values. So we have 3 plus 3 squared divided by 2 times 9.81 is equal to H2 plus 27 squared divided by 2 times 9.81 times 3 squared, that is our B squared, times H2 squared. Again, we don't know what H2 is. And to this, we're going to add 0.3, which is the height of the bump. So if we take this entire expression here and we evaluate each of these numeric values, what we'll end up with is 3.1587 is equal to H2 plus quantity 4.1284 divided by H2 squared. So we have an equation just in terms of H2. Let's go ahead and multiply both sides by H2 squared, because I want to put this in the form of a polynomial. It'll make it a bit easier to work with. And when I do that, what I should end up with is the following. I will end up with a cubic polynomial in H2. So it's going to be H2 cubed minus 3.1587 times H2 squared plus 4.1284 is equal to 0. So how can I go about finding the depth at the bump? Yes.
Substitute H2 squared for just a single variable and then solve it using the quadratic equation and plug it back in.
Close, but I don't think that will work. So it's a cubic polynomial. So there will be, first of all, how many solutions are there for H2? There's 3 solutions for H2, so that's kind of weird. So this is a cubic polynomial. So to solve for H2, we find the what's of this polynomial. We find the roots of this polynomial. Let's go ahead and do that. Again, Excel is not a great tool for solving the roots of polynomials. I'm going to use Desmos, but you can use your calculator, or if you know a programming language, you can find the roots using a programming language. So let me go in here and type in our equation. And we'll see if we can find the answer to our riddle. So here we have x cubed minus 3.1587 times x squared plus 4.1284. And you'll see that there are 3 roots. So let's go ahead and write down these roots. One of them is negative 0.997. The other is 1.659. And the other is 2.496. So let me write those down. So our depth is going to be one of those 3 values. Negative 0.997, 1.659, or 2.496. Okay, so the first one we can essentially throw this answer out. This answer is non-physical. We can't have a negative depth. So this is non-physical. And we're left with 2 different answers. So let's go ahead and just see what we get when we add the bottom height of the bump. So I'm going to add 0.3 to each of these. So this is delta Z naught. And what I'll end up with is H2 plus delta Z naught is equal to one of the following, either 1.959 meters or 2.796 meters. Okay, so first of all, we can conclude something right away. What is the answer to our mystery problem from before? What happens to the water surface? Which one? Does it go up or does it go down? It goes down. So for either one of these answers, the water surface is going to be less than 3 meters. So the water surface actually goes down. So if you got the correct answer, give yourself a pat on the back. Or if you said this is a trick question, you can also give yourself a pat on the back because as it turns out, there's more to this story. So we have 2 different answers here. What do you think these 2 answers correspond to? Why are there 2 different values for the depth that it can take? Yes. Sorry? So it turns out that H2 can be only one of these 2 for any given flow condition that you're encountering. Why might there be 2 alternative depths that the flow can take? maybe think back to lab 4. So for a given discharge and for a given channel geometry, it turns out there are 2 alternative depths that the water can take. And they correspond to 2 different conditions. So based on lab 4 and from your previous experience in fluid mechanics, can you guess what these 2 conditions are? Very good. So you may remember from fluid mechanics, subcritical and supercritical flow. So the flow can be traveling at either one of these conditions. It turns out that this answer here corresponds to subcritical flow. And this answer here turns out to correspond to supercritical flow. So I'm going to review subcritical and supercritical flow shortly, but just keep in mind that the answer can be either one of these 2. It happens to be one of them, but right now we don't have enough information to determine which is the correct answer. So we're going to need to take a little detour into subcritical versus supercritical flow first, and then we can determine what the correct depth is at our flow transition. Are there any questions before I continue? Questions before I continue? Okay, so I'm going to review subcritical and supercritical flow. We're going to need to understand what they mean in order to answer this question. So the first concept I want to review is the concept of specific energy. We're going to need it to talk about subcritical and supercritical flow and what they mean. So specific energy, you can basically think of it as the energy that can be traded between potential energy, i.e. the energy associated with the depth of the water, and kinetic energy, i.e. the energy associated with the velocity of the water. So for flow in an open channel, the specific energy is equal to H plus U squared over 2G. So it's basically, if you take the energy equation and you just remove the component associated with the channel bottom, associated with that gravitational force, that is the specific energy. So E here, this is our specific energy. So you can essentially think of it as the energy that can be traded between these 2 quantities. So the water, as it moves, may adjust the amount of energy that's in the potential component versus the kinetic component. So for a given channel geometry, each specific energy curve corresponds to a constant discharge. So if you have a fixed channel geometry, a given discharge will have its own specific energy curve. So this will be more clear in a second when I start drawing the specific energy curves. Is this something that you talked about in fluid mechanics? You talk about specific energy. Yes, no? No? No. Okay. So we'll make sure that you get it today. All right, so let's go ahead and draw out the specific energy for flow in an open channel. So I'm going to draw a channel cross section over here on the left. And on the right, I'm going to draw a graph. So in this channel, for a given discharge, we can have flow traveling at different depths. So for all of the lines I'm about to draw, all of these lines are operating at the same discharge, just at different depths. So as the depth decreases for a given discharge, the velocity will increase because they all have the same discharge. So let's say we have a depth here. We have a depth somewhere down here. We have a depth somewhere down here. So again, all of these depths here, these are at the same discharge, but different velocity. And for a given discharge, we can draw the specific energy curve corresponding to each of these different depths, okay, as the depth varies from the bottom of the channel to the top. So in this graph here, we're going to be graphing the depth of water on the y-axis. And on the x-axis, we are going to be graphing the specific energy, which is equal to h plus u squared over 2g. Now note that if the channel geometry is constant and the discharge is constant, specific energy becomes just a function of the depth. So this will be h plus q squared divided by, let's just say it's a rectangular channel. So this would be 2g b squared h squared. So for a constant discharge and a fixed geometry, the specific energy will just be a function of the depth. So let's go ahead and plot out the specific energy corresponding to each of these depths. I'm going to draw a diagonal line here just to help me draw the plot. And if we plot out this specific energy function, this specific energy curve as a function of the depth, it will look something like this. So each of these depths over here on the left corresponds to some point on our specific energy curve. Let me just draw these lines here from our depths indicated on the left to our specific energy curve over here on the right. So let's say this is H1, this is H2, this is H3. So again, all of them are at the same discharge, but at different depths. So this diagonal line, this indicates that the specific energy is equal to the depth. Okay, so that diagonal line is the line where our specific energy is equal to the depth. That means that for each of these points on our specific energy curve, we can partition the specific energy into the point that's left of that diagonal line and the point that's to the right of that diagonal line. And the portion on the left is equal to the depth. So that'll be H1, H2, H3. And what will the portion to the right of that diagonal line be? The velocity head. So it'll be, excuse me, this will be U1 squared over 2G. This will be let me draw it over here. This will be U2 squared over 2G, and this will be U3 squared over 2G. So you'll notice that as the depth increases, you'll have a much larger component of your specific energy in the depth component and a much smaller component in the velocity component. At the shallower depths, you'll have a much larger component of your energy in the velocity component and a smaller component in your potential energy or depth component. So again, the specific energy kind of tracks the energy that can be traded between potential energy and kinetic energy. At shallower depths, you'll have more energy in the kinetic energy component. At larger depths, you'll have more energy in the potential energy component. Are there any questions so far on specific energy? So another thing you'll notice is if you take a point somewhere on the x-axis, so if you take a given specific energy, we can draw a line. And you'll notice that for a given specific energy, there are two depths that the water can be traveling at. So these are our alternative depths. So for a given specific energy, there are always two depths that the water can be traveling at, except for at one point. Right? At the very extreme point of this curve here, the water is traveling just at a single depth. This point here is called the critical depth. Is this something that you talked about in fluid mechanics? Critical depth, is that something that you covered? All right, so we'll talk about the critical depth and what it means, but at every point other than the critical depth, for a given specific energy, the water can be traveling at two different depths. So the critical depth delineates the two flow regimes that are possible. If we're traveling along this specific energy curve, anything above this critical depth, this is subcritical flow. And anything below this depth is supercritical flow. Yes.
If we were only given the energy, if I guess the system, we couldn't tell you the depth at which it was operating. Well, we could tell you there's two depths, but we wouldn't know which unless we knew the critical.
Yes.
Okay.
Yeah. So if you only have the total energy, you won't necessarily know which regime it's operating at. But I'm going to show you how we can go back and solve our initial mystery problem once we understand how to differentiate supercritical and subcritical flow. So for right now, what you need to know is that for any given specific energy, the flow can be traveling at two depths. except for at a critical point, the critical depth, where the specific energy is at its minimum. Anything above the critical depth, so if the depth is larger than the critical depth, you have subcritical flow, where the energy is mostly in the potential energy component. If the depth is less than the critical depth, you have supercritical flow, where most of the energy is in the velocity head component. All right, so let's say that we have a given discharge and a given channel geometry, and we want to compute the critical depth. We want to find what that critical depth is. How can we do it just looking at this graph here? Let's say we have our equation for the specific energy, and we want to find what the critical depth is. We want an expression for the critical depth. How can we go about finding that minimum point? Very good. So we're going to go back to calculus. We're going to take this expression for the specific energy. We're going to differentiate it with respect to the depth. And we're going to set it equal to 0. And from that, we can find what the critical depth will be. So let's go ahead and do that. If we want to find the critical depth, we differentiate the specific energy with respect to the depth of water in the channel, and we set it equal to 0. So let's do that. We're going to take dE by dH. We're going to set it equal to 0. So this is going to be equal to d by dH of quantity h plus u squared over 2g. So first of all, if we take d by dH of h, what do we get? 1. Okay, first part's not too bad. Second, let's take d by dH of u squared over 2g. Okay, we're computing the total derivative here. So to compute this derivative, the first thing we're going to want to do is express the velocity in terms of the discharge and the area. Okay, so we're taking the derivative of this expression here with respect to the depth. Which terms here can we pull out of this derivative? Okay, very good. So we'll pull out 2g, that's just a constant. And why can we pull out q? Why can we pull out q? Very good. So for a given specific energy curve, remember that we're talking about a constant discharge. So q we can also pull out. So we'll take q squared over 2g times d by dH of 1 over a squared. And we know that the cross-sectional area will be a function of the depth. So we need to compute this derivative here. So let's not assume a particular hydraulic geometry. Let's try to do this just for a generic cross-sectional area. Turns out we can do that. So we'll have q squared divided by 2g times d by dH. And instead of 1 over a squared, I'm going to write it as a to the negative 2 power. All right. So what we're going to do here is we're going to invoke the chain rule. If you think back to Calc 1 or 2, I don't remember which one. We have some function f of x. The derivative of f with respect to x is equal to the derivative of f with respect to some other function dg. Some other function g times dg by dx. So what we can do is we can take the derivative of a to the negative 2 power with respect to a times dA by dH. So this becomes q squared over 2g times d a to the negative 2 power by dA times dA by dH. And this is an application of the chain rule, a super useful rule. All right, so what is this derivative here just from the power rule? Right, so it'll be negative 2a to the negative third. So we'll have q squared divided by 2g. Let me just rewrite out the whole thing. So this will be dA to the negative 2 divided by dA, sorry, not divided by, dA to the negative 2 by dA times dA dH. This is going to be equal to q squared divided by 2g times quantity negative 2 a to the negative 3 times dA by dH. Now there's one last thing we need to do, which is we need to come up with an expression for this dA by dH. So I'll let you think about that for a second. So let me simplify this whole expression here. This becomes negative q squared divided by g a cubed. So the 2's cancel here, and we end up with negative q squared divided by g a cubed times dA by dH. Okay, so what does dA by dH represent? So it's the change in area of flow with respect to the change in height. So let's draw out our channel here. We have some water level in the channel. And this water level, let's say it's changing by some infinitesimal amount, dH. So there's some water level H, it's changing by some infinitesimal amount dH, and we want to know what is the change in area for a given infinitesimal change in the depth dH. So the change in area will be equal to dH times dA by dH. So just thinking about the geometry of the channel, what's another word or what's another term for dA by dH? Did I hear someone say it? What do we need to multiply by the infinitesimal change in the depth to get the infinitesimal change in the area? Sorry? The length of this surface here, which will be called what? Sorry? The top width of the channel. So dA by dH, this is the top width of the channel. So this is an important identity to remember in hydraulics and computational fluid dynamics. The change in area with respect to the change in depth is equal to the top width of your channel. So to summarize, d by dH of u squared over 2g is going to be equal to negative q squared times the top width divided by GA cubed. So let's put it all together. Okay, I have just enough time to finish here. So we have that 0 is equal to dE by dH, which is d by dH of H plus U squared over 2G. DH by DH is 1. And as we just found out, D by DH of U squared over 2G is equal to negative Q squared times the top width divided by GA cubed. So we can also express this, note that Q divided by A is the velocity. So this can also be written 1 minus U squared T over GA. And this gives us our condition for critical flow. Critical flow occurs when U squared T divided by GA is equal to 1. And this applies for any hydraulic geometry. This is our condition for critical flow. So we have that critical flow occurs when this quantity here is equal to 1. Does that remind you of anything from fluid mechanics? Critical flow occurs when something is equal to 1. That's something that you covered? Oh, yes. Not Reynolds number, another number. Yeah. Froude number, very good. So we can modify this expression to arrive at a quantity that's kind of analogous to the Reynolds number that allows us to determine whether the flow is subcritical, supercritical, or critical. If we take the square root of this entire expression, we end up with the Froude number. So taking the square root, we end up with a diagnostic number called the Froude number that lets us determine whether the flow is subcritical, critical, or supercritical. So if we take the square root of our previous expression, we get velocity times the square root of the top width divided by the square root of acceleration due to gravity times the area, cross-sectional area. And we can determine the flow regime by looking at the magnitude of this number. So if it is less than 1, your flow will be subcritical. If it is equal to 1, you will have critical flow. And if it's greater than 1, you will have supercritical flow. So the Froude number, which comes from this derivation, we can use to determine whether the flow is subcritical, critical, or supercritical. So I'm about out of time. At the start of class next time, we will resolve our mystery problem. Until then, I can see you at office hours today. And remember that you have a couple homework problems due tomorrow.